I'd like to introduce you to Michael Rossol at NREL. He'll be here to talk about the Open Energy Data Initiative. And Michael, I'll leave it to you.
All right, thank you so much, and thanks for the invitation. So yeah, my name is Michael Rossol. I am a data engineer at the National Renewable Energy Lab in Golden, Colorado. And I'm going to be talking about our Open Energy Data Initiative. This is a DOE-funded, 3-year funded project under the Solar Energy Technology Office that is focused at creating a data lake up on AWS to disseminate a lot of our high-value public data sets that have been created under DOE projects. Before I get started, I just want to acknowledge 2 of my collaborators on this project, John Oedi at the HDF group. We've been working closely to use the HSDS service, and then David Rager, our cloud architect at NREL. So as I mentioned, the Open Energy Data Initiative is aimed at improving and automating access to high-value data sets that are produced under the U.S. Department of Energy programs and offices and national laboratories. So the reason that we are trying to migrate to the cloud is that historically, NREL or DOE has used kind of a data repository approach to making publicly available data accessible. So data is uploaded to data repositories. The big one is OpenEI, and then people can download that data to their local machines. This has worked great for older, small CSV size data sets. It doesn't work very well when you have extremely large data sets, like the ones I'll be talking about today. These are our large resource data sets that are in each individual file is about 1 terabyte, and we have hundreds of terabytes of data in total. So what we'd like to do is kind of flip the paradigm, and instead of having people bring the data to themselves, it's bring data to the people. So we're partnering with different cloud vendors. Currently, we're building out our data lake on AWS. And the idea here is we host all of the data in a single location. We build cloud optimized tools around that data, and then we can have people come use the cloud infrastructure to collaborate and really kind of push the boundaries of innovation by having everyone use the same ecosystem and the advanced cloud computing architectures. So this is kind of our visualization of the data lake. We like the actual lake.
Michael, excuse me. We're still seeing, at least I'm still seeing your first slide, and it's
really?
Not, yeah, and it's not a presenter. It's like probably presenting you or something.
Interesting.
Yeah. So you're on the 4th slide, and I don't know if it's me, but does everyone see the slides?
Thank you for the interruption. I don't know what Zoom is doing. Let me try again. All right, is that better?
It's better
It
now.
is slide 2, yes, thank you.
Yeah,
okay.
Too, sorry.
Very strange. All right, so yeah, you didn't miss much. So yeah, what is OEDI? We really like this data lake, this lake motif. And so the idea here is that all of the data is put into the lake, and then people come and camp out at the lake. So they can bring their own data, add it into the ecosystem, and they can bring their computational tools and work in the same environment. So what are we trying to enable? We're really trying to enable the entire public sphere of data analysis. So research in academia, research in the private sector by making our data available public. We have very, very large data sets, which we think are very helpful for machine learning. And then what DOE is really hoping is that by making a lot of these renewable energy data sets available, we can push innovation and analysis in the fields of renewable research. So this is kind of what our data lake looks like. Currently, as I mentioned, we're working on AWS. We are partnering with AWS's Public Datasets program. And what that allows us to do is host data on Amazon S3 for free. So this is a program that they've had for over a decade, where they pay for the storage of publicly developed data sets by a lot of federal entities, NOAA, NASA, DOE, et cetera. And then what we've done is we've built these cloud optimized tools on top of it. Today, I'm going to be talking about the HDF Group's tool, HSDS, but we also are using some of Amazon's tools, Amazon Glue, or AWS Glue, Amazon Athena. And the idea here is that we've built these tools to help people access these data sets that we're putting on S3 for analysis in Tableau, Jupyter, Python, etc. Okay, so what is the big problem that we're trying to solve, and why have we been working with John Reedy and the HDF Group with HSDS? So our two flagship data sets that really were the driving force for OEDI is the National Solar Radiation Database. This is now going on over 20 years of solar radiation data for the Western Hemisphere. The large 20+ year data set is at 4-kilometer spatial resolution, 30-minute temporal resolution, and we store it in HDF5 format. I'll explain why on the next slide, but it's about 46 terabytes in size. We more recently, with the addition of the new GOES satellites, which is what we use to calculate the irradiance data, we have 5-minute 2-kilometer data for 2018 and 2019. Each of those data sets are about 20 terabytes each. The analog for wind resource is our wind toolkit data. This right now covers 2007 through 2014 for North America at 2-kilometer and 5-minute resolution, and it is a massive 424 terabytes in size. So as you can see, these are massive data sets. There's no way you would want to download them to a local machine. Each file is about a terabyte at the smallest, and just transferring them around S3 can take up to 9 hours. So really not a great way to be accessing this data. So our solution has been a phenomenal collaboration with the HDF Group to use their highly scalable digital service. So this is, as most of you are probably familiar, their cloud optimized solution for the HDF5 file format. It uses a compute service running on either a Kubernetes cluster or on EC2 that has a bunch of containers that help access the bits of data that you're interested in the HDF5 files. So how are we leveraging the HDF5 file format? The reason that we decided to use HDF5 to start with is that we really like that it can store multiple types of data, very large data, and that it's self-annotated. So this is just kind of several of the data sets available in our Wind Toolkit files. We have a 2D vector with the lat-long coordinates. We have a data table, which is the metadata for all of our locations. And then we have all of these time series arrays. So we have gone away from like the source data being an actual perfect gridded array and converted it to time series format because this is what's of interest to our modelers. We want to use this data to compute time series renewable generation. So we're really interested in what is the full annual time series of either wind or solar resource for a single location or multiple locations. So we have these 2D arrays of time by location, and you can determine the locations from either the coordinates or the metadata table, and then you can determine the time steps from a time index vector. So we really like that we can store multiple shapes and types of data in the same file. As I mentioned, these files are massive. They're about a terabyte in size. So by dictating the chunk size, we can really ensure that reading from the files is performant for the types of analysis we want to do. And then we also like that we can self-annotate multiple levels of the file. So almost every single one of these data sets has attributes giving units, descriptions, scale factors if we are scaling them to integers, etc. It's really nice that we can kind of deliver a file that is fully self-annotated so that all of our different modelers inside NREL and in the public can very quickly understand what it is that is in the data set. So then how are we leveraging HSDS? We are using the direct read approach in HSDS, and this works really well with how we're using S3. So we have multiple S3 buckets within the public dataset program that have the source HDF5 files. These are the files that we've created at NREL on our HPC and use for our analysis internally. So we've just copied those straight up to S3. Again, for anyone that's crazy enough to want to download 500 terabytes of HDF5 files, they're there. But then we've loaded the metadata into HSDS. So we have a dedicated public HSDS bucket that is linked with Kitalab. and is available for anyone to point to if they spin up their own service. And then we do have a service available to the public that's paid for and hosted by NREL that allows people to play with this data. So for those of you not really familiar with HSDS, how this works is the service uses the metadata that has been and the chunk information that we've loaded in, but pulls the data directly from the H5 files that are stored as objects on S3. So these are the resources that we have for anyone that's interested. We have a bunch of buckets with the source data. This UMCM data is a coupled model of Hurricane Ike and Hurricane Sandy. We have the NSRDB data. This covers what I talked about, the Western Hemisphere, as well as we have some new data for India, for most of Central or most of Africa and the Middle East from the Meteosat satellites. We also have a new data set of distributed acoustic sensing data that was produced by the Geothermal Technology Office. We have our Wind Toolkit bucket, which has data for North America, as well as some one-off wind resource data sets for several countries in Asia. And then we also have a new hindcast of US offshore wave data. So this is going back from 2010 through to 1978 currently for the West Coast, but we're working on adding data for all of the US coastline, including Hawaii and the islands. So all of this data has been loaded into our HSDS bucket. This bucket again is public, so if you want to access it through KetoLab, you can, or if you want to spin up your own service and access our data, you can just point to this bucket. And then this is our endpoint. It does require an API key, so you can sign up and get one at developer.nrel.gov, but this will allow you to kind of get an idea of what data we have available in HSDS. One of the unique advantages that I've found of HSDS is that it allows us, because we're doing direct read, to source data from multiple individual H5 files. So this is a problem we've run into locally on our HPC. A great example is this 5-minute Wind Toolkit data for CONUS. It's about 17 terabytes per year. So we're looking at if you try to store that in a single HDF5 file, we can't even upload it to S3. It's just way too big. So what we've done is we've broken it up into multiple files by hub height. So depending on how many heights we have in the data set, you're looking at over 10 different individual files. This is not great for our users locally. We've actually built some Python wrappers to make it a little bit more seamless for accessing data across all the files. But HSDS allows us to do this when we load it in. So what we can do is we can load all of the data sets from all the files into a single HSDS file pointer, and it's just sourced on the back end by HSDS from all of the individual objects on S3. So this is one use case that we found to be really, really helpful, where we can control how the data is loaded into S3, but it provides a really seamless experience for the users through the service, which has been great. Some of the unique challenges that we are currently dealing with data sets of these size is auto scaling. So our usage is quite stochastic. We have people that kick off an analysis and they want gigabytes of data for a couple hours, and then our service isn't touched all weekend. So it's really not great from a cost standpoint. We just have an EC2 instance running 24/7, 365. Sometimes it is overloaded and we're returning 503 errors. Sometimes it is completely stagnant and not being used. So we've been working with John to figure out solutions either through Kubernetes or AWS Lambda on how we can kind of handle the stochastic usage in a more performant and cost-effective way. The other place where auto-scaling is going to be really important is as we start to migrate some of our internal analysis to AWS. We want to really leverage HSDS's parallel framework for really large requests. So right now we have a finite amount of bandwidth with the size of our EC2 instance. It would be really great, again, if we want to access every single data point in the United States, which is about 2.5 million sites. How can we leverage HSDS and auto-scaling to make that request, get all the data we need, send it out to a bunch of different containers to do the analysis, and just pay for that compute when we need it, instead of having to spin up a massive number of containers and then spin them down after we're done with our analysis. Loading large data sets can also be difficult. We've found that it's easiest to read the metadata from files locally. So when we load data into HSDS, we will determine the chunk information on our HPC and then push that to our service on AWS. This isn't always the most convenient. We are fortunate that we have an HPC. We're also fortunate that we have the storage needed to be able to have a copy locally and on AWS. But if we tried to load a file from S3, it is painfully slow just because these files are so large. The other problem, and this is fixing data bugs. This is really easy when we have loaded the data directly into HSDS. We were doing this originally, but as you can imagine, when you have 424 terabytes of data, that is billions of individual chunk objects. It becomes really, really hard to manage when you have a file locally that you have to then reload in, or managing those two formats. We found that using the direct read approach really works well for us, because we can just make fixes locally and push them to S3. The only problem there is every time we make a fix, we have to copy the entire file over to S3, and then we have to reload the data into HSDS. That last part is quite quick, maybe takes a couple hours. Transferring the fix file up to S3 can take days. So there still are definitely some challenges with these massive files and how to best manage having a local copy and an HSDS copy that we are playing with. So with that, I will be more than happy to take any questions. I've got my contact info, both my collaborators. These are some websites. So data.openai.gov is our data catalog for OEDI. We've got documentation on all of the different data sets that we have up in OEDI, and then we've got some HSDS examples that provide information on our service and the data sets that we've loaded into HSDS, as well as pointing to our collaboration at AWS for the Open Datasets program. And I'd be more than happy to take any questions.
Are there any more questions? Well, I think that's it. Thank you, Michael, for the presentation. We really appreciate
Thank you guys again
you.
for the invitation.